Welcome back for the lightning talks. So how this is going to work is we're having 7 speakers go. The first 2 are on Zoom, and then the next 5 are here, and everyone will speak for 5 minutes, and we'll take up to 1 question per speaker. When you talk in person, you got to clip on this microphone so that the Zoom can pick it up, and it should also amplify your voice a little bit in the room. But that's not relevant for people who are on Zoom, and just for the speaker on Zoom. So on Zoom, one more time, you just tell me to hit the slide, and I'll hit the slide for you. All right, whenever you're ready, Joris.
Right. So, well, good to be there, at least virtually. And I want to use my time to talk about the amplituhedron, well, in fact, and how to take this to the limit. And that is based on recent work with my supervisor, Rainer Sinn. And I want to do so by means of an example, which is going to be the pizza geometry on the next slide.
All right, I'm trying to find the picture of.
Very well. Yes, so I want to use my 4 minutes to basically explain this picture to you, and this is dubbed the pizza geometry, is an example of a positive geometry, and it is fairly well known to the community. And we really, in this project, we took a spin on it and generalized this and related to this to the amplituhedron. And so we can go to the next slide. And of course, Marcus has already today introduced us to the amplituhedron.
Sorry, technical problems. We'll change the slide in a second.
Okay, thank you. And so I'm going to do only a quick rundown and try to direct the attention on the essential parts on this slide. And really, what we want to have is, well, we take a totally positive matrix Z. This is going to induce a map that is well defined from the totally non-negative Grassmannian GRKN to the Grassmannian GRK K plus M, basically by multiplying this with the left by matrices. And then Yara and Nima in 2013 or 14, they defined this image to be the amplituhedron. And as Marcus has told us, this captures important, well, scattering amplitudes in the super Yang-Mills theory. And really what I want to do here in the setup is just briefly say, okay, do an example here, and this is going to tie in with the picture you've just saw a second ago. So you take a Z matrix. In this case, we set n equals to 4, m equals to 2, k equals to 1. So the Z matrix is a 4 times 3 matrix. And you fix the first row to be the origin in an affine patch. So it's really, we should think of this point as 1, 0, 0. And then you choose 2 other points, Z1, Z2, that lie on the moment curve, and a fourth point. They're all 1 point. And then if you take this Z matrix, really, you know, the amplitude is not too bad for these choice of parameters. It's really just the quadrilateral whose vertices are labeled by your rows of the Z matrix. So, and then already in the original paper about the amplituhedron, Yara and Nima wondered, well, what happens if you send those parameters to infinity? In particular, what happens if you send n to infinity? And we set out basically to answer at least part of this problem. And I'm going to show you how to think of this on the next slide. Well, first look at the top left corner here, and you see that is already our quadrilateral that is inside this pizza geometry that was the green shaded part. And the vertices, remember, were labeled by our points on the moment curve and the 0 and 1 point. Therefore, the labeling of this special line cutting through the circle S01, and the circle is labeled by C2. And well, if you send now n to infinity, what really is going to happen, and I draw like another 5-gon inside this half disk. Well, if you sample more points on the moment curve, which is the circle in this case, then you essentially are trying to inscribe this half disk. And in fact, in the limit, you're just going to sample all of the half disk. And Actually, we call this the limit amplituhedron. That is, we take the union of all such amplituhedron, that is Z matrices for all choices of n, and take its union and show our main result of Reiner's and I's papers is then really to show that this is a positive geometry. And of course, that was already known for the case k equals 1, but we really generalize this to any k amplituhedron. And really what you think of is that the semi-algebraic set that is really important here is given by the generalization of the circle, which is just the rational normal curve of degree ck, and the special line through 0 and 1. And I'm using air quotes here, and they do some heavy lifting, but this is as far as we went in this paper, and thus we solved one of the problems mentioned by Nima and Akani Hamid like a decade ago. And you can read more about this in the paper or message me, even if you can't talk in person. All right. I think that's my 5 minutes.
Anybody have a question for Joris? All right. Thank you. And now next is Elise, who's also talking on Zoom from the University of Minnesota. Elise, give me just 30 seconds to see if I can mess with
I think you have to minimize it.
All right, you should be good.
Okay. So thank you so much for the opportunity to speak, and thank you to the organizers for making this summer school happen. So I'll be telling you about a toric analog for Green's rational function of a poset, but first I want to tell you about Green's rational function for ordinary posets. So that brings me to the next slide. Okay. So the posets that we'll be looking at are finite, and for each element that I have in my poset, I have a corresponding indeterminate. And in 1992, Curtis Green introduced this rational function in order to give a combinatorial proof of the Murnaghan-Nakayama formula. So what does this rational function look like? Well, we take a sum over the set of linear extensions of the poset, and for each linear extension that we have, we get a corresponding rational function that always has 1 in the numerator. And in the denominator, we get this product of linear factors where we just inch our way up our linear extension. So here I've included 2 examples of relatively small posets, and we can observe there's some nice simplification happening. And so you might wonder, is this nice simplification representative of some more general phenomena? And the answer is yes. So in particular, Curtis Green showed that if you look at a specific family of posets, these strongly planar posets, you will get some nice simplification. And then later, Boucicault, Fauré, Lescu, and Reiner added on to Green's results by introducing a geometric and algebraic perspective. So for the geometric perspective, what they showed is that Green's rational function is actually a specific instance of some polyhedral cone valuation. The algebraic perspective, well, if you start with a poset, you can associate to it some affine semigroup ring and compute a Hilbert series, do some algebraic manipulation, and then you would see that this Green's rational function would fall out of that computation. So having introduced these new perspectives, they were able to build on Green's work. They gave a characterization for the vanishing of this function. They were able to pin down a smallest denominator. But for me, I really care about these toric posets, which brings me to my next slide. Thank you. So what are they? So posets correspond to chambers in a graphic hyperplane arrangement. These toric posets correspond to toric chambers or connected components in a toric graphic hyperplane arrangement. So that's where these toric posets are getting their names. It's really from this toric graphic hyperplane arrangement. And so we have this geometric definition of a toric poset, but we also have a combinatorial one, which I will use today. So a toric poset you can think of as a source sink flip equivalence class of acyclic quivers. Here by acyclic, I mean that I have no directed cycles. And this source sink flip equivalence class, how we're going to reach everything is we're going to start with an acyclic quiver, find a sink or a source, whichever you prefer, and flip, let's say, a source to a sink. So edges directed out to edges directed in. You're going to do this one at a time, and you get a whole family of acyclic quivers. And I want to emphasize that this whole set is one toric poset. Okay, and so there are certain analogs, certain properties that carry over to the toric poset setting. One of them is the notion of toric total extensions, which is the toric analog of a linear extension for an ordinary poset. And for these toric total extensions, they are now cyclic equivalence classes. So if we look at this toric poset in the middle of the slide, the set of toric total extensions, and I'm not going to tell you how to find them, is the set on the bottom of the slide. So now we're ready to introduce the toric analog of Green's rational function on the next slide. Okay, so the definition looks pretty similar to the ordinary poset case, except now we're taking a sum over the set of toric total extensions. And in addition, in the denominator, we get this added linear factor, what I like to think of as this wraparound term, this xwn minus xw1, to account for the cyclic nature of these toric posets. And so a lot of my work has been providing analogous results to Green and Boucicault, Fauré, Lescaut, and Reiner. But as a byproduct of this work, and one result that's more in line with the themes of this summer school is the following. If you evaluate this rational function on the toric poset that you see on the right, and I've only drawn one representative, you're able to recover an equation that comes up in scattering amplitude computations called these Kleist-Quiff-Shuffle relations. And in addition, I want to point out that the denominator of this psi-tor function appears as particular factors in scattering amplitude as well. So in general, I'm coming at this, at this work from a very combinatorial perspective. I would very much like to learn more about the connections between this Green's rational function the toric analog that I've introduced, and the physics side. So thank you so much for listening. And if you go to the next slide, you'll see a cute toric poset.
Thanks, Elise. Question for Lauren.
I was just wondering if there's a connection to any kind of nice family of polytopes.
Polytope one would consider. I'd love to know about it.
Right, great. Thanks so much.
Yes, so hi, I'm Veronica, and I want to tell you quickly about a nice project called Kinematic Stratifications. This is joint work having Frost and Berg. Motivation came from particle physics, and we want to describe configurations of momentum vectors of particles. Think of them as invariants on the rotation. And so really, instead of working with the coordinates of the vectors, we want to work with their Mandelstam invariants, which are their pairwise inner products with respect to this Lorentz metric. Okay, and the toolbox that we want to use from math is a little bit of combinatorics. And so we want to combinatorially describe these configurations. And for this, we are going to plug in this Mandelstam invariance into a symmetric matrix. And we're going to define a semi-algebraic set of the space of symmetric matrices, which we call the Mandelstam region. And these are going to be rank R symmetric matrices, which arise in this way. And now what we want to do is somehow stratify this semi-algebraic set. That is to write it as a disjoint union of some smaller cells, which can be indexed by some nice combinatorial object that helps us understand how these different cells interact with each other. And basically what gave us the motivation to do this project is that from the very definition, there is a connection with something that has been independently studied in combinatorics for different reasons, and this is Lorentzian polynomials. And so given a rank R symmetric matrix, we have three different equivalent ways of thinking about it as arising as a representing a configuration of particles. This is, we can view as principal minors, and then the signs have to be alternating. But then also this is equivalent to us having non-negative entries in the diagonal and it having Lorentzian signature. This last thing, when we extra impose that all the entries are positive, is exactly the definition of degree 2 Lorentzian polynomials. And while using this alternating sign of the principal minors, we can split our Mandelstam region according to the signs of the entries of S, which gives us a way to write this Mandelstam region as a union of smaller spaces, which are basically just signed versions of Lorentzian polynomials. But the interesting part is when we start imposing more natural conditions that come from physics. So the first thing we consider was what happens when you have massless particles. And in this case, we can stratify our region via signed rank 2 matroids. So this is just a rank 2 matroid, and then we consider some signs in the ground set. And then this gives us a very nice stratification and also a nice poset structure to understand our set. If furthermore the particles satisfy momentum conservation, we can get strata which are indexed by sign matroids which satisfy a balancing condition. And basically the whole point of our project is that we characterize when these strata are non-empty, we give dimension formulas for each of the strata, and we also give some counting formulas for the number of strata per dimension and rank. And just to finish, so a natural question is what happens with massive particles? And here the problem becomes a little bit more complicated, but you sort of have that the massless case is a bit of a limiting behavior of a generic situation. And I wanted to include this picture because exactly this thing was what Stanley Mandelstam drew in his original 1958 paper where Mandelstam invariants were introduced. Yes, and that's it. Thank you.
There a question for Veronica?
For the sign matrix. So how do you define that?
It's just a matroid and you have a sign on the ground set. There's no extra condition.
It's not a matrix oriented.
No, it's not. It's something that's weaker.
Next up is Bella.
Your issue about
Okay. Well, thank you, Jonathan and Mateo, for organizing the lightning talks. I'm going to tell you today about a class of combinatorial objects that arose in the context of birational geometry that also have an interpretation in terms of on-shell diagrams. So these objects are called hypertrees, and they're defined as a collection of 3 tuples on some vertex set that satisfy 2 conditions. One is some appearance condition that every index appears in at least 2 triples, and there's also some spreading condition that no matter what set of my triples I choose, I find in that set sufficiently many indices. So these hypertrees were introduced in 2010 by Anna Maria Castrove and Genia Tevelev, where they prove that hypertrees parameterize effective divisors on the moduli space M0n, and hypothesize that all effective divisors besides boundary divisors are those coming from hypertrees. And the way you get these divisors is that you take the closure of the locus in M0n that you obtain by choosing a planar realization of a hypertree and then projecting onto P1. A few years later, it was observed that collections of triples label reduced non-planar MHV on shell diagrams. And much more recently, it was an observation of Freddie Cachazo and Nick Early that all of these hypertrees in the sense of Kashtaray and Tevelev give such labelings of on-shell diagrams. So this raises the question, how can we ask about the geometry of this connection? Perhaps is there some quantity that has some meaning in both contexts? And one such quantity is the maximum likelihood degree. So if you write down the CHY scattering potential, this is some log likelihood function, you can ask how many critical points does this have on M0n. The number of critical points is called the ML degree. And right, if we model M0n as some quotient of an open Grassmannian, we can literally write down a chart and label this set of coordinates by the indices in our hypertree. So we have an ML degree associated to a hypertree. And it turns out there's a construction of an infinite family of hypertrees that have ML degree 0. And in fact, these hypertrees correspond to divisors with more than one irreducible component. So there's this sort of add a vertex construction where you keep some kind of degeneracy. And as you'd expect, you can argue that this family has ML degree 0 by induction, where we have the happy scenario where our base case actually appears in R3. So there are some associated varieties that are linear. So counting our ML degree involves enumerating the bounded regions in some hyperplane arrangement, which we can look at right here and see that it's 0. And we're also working to smooth very affine varieties. So our ML degree is also counted by the Euler characteristic. And in fact, it's possible to find a fibration between a variety associated with a hypertree on n vertices and one associated with a hypertree on n+1 vertices to affirm that this is in fact an infinite family, and in fact, one grows in kind of a Fibonaccian way of hypertrees degenerate in the sense that their ML degree is 0 in the scattering world, as well as degenerate in the sense that they correspond to reducible divisors on M0n. So I thank you for your attention.
There are notion of hypertrees for other moduli spaces like GR3, and Torus.
Yeah, that sure is a great question. Well, there isn't. I guess there isn't a sense of hypertree. There is maybe a sense of some related object that you could define that would have some of the same properties that you want, but not of. It goes well beyond the work of Kashtaray and Tevelev.
Yeah. You could ask other questions afterwards. Not limiting to only one question.
All right, so I want to tell you all a little bit about geometry and combinatorics of a class of matrices called P-matrices. So what P-matrix is a complex n by n matrix, all of whose principal minors are real and positive. So you can think of this as PSD matrices if you're familiar, but without the condition that they're symmetric or real entries. And up to closure, you can consider non-negative principal minors. So these were introduced in the 60s. One reason to maybe care about them is because up to Euclidean closure, they include positive semi-definite matrices. There's a few reasons to care about PSD matrices if you don't already. They also include totally positive matrices. Principal minors are in particular minors, so those are in there. Another reason you might care about these things are some results saying that combinatorial things like spanning trees, perfect matchings, probabilities of edge inclusions in the uniform distribution on perfect matchings with some appropriate adjectives can be counted via determinants and principal minors. One question you can ask is just kind of in general, when are the principal minors of a matrix positive or non-negative? Okay. Curly P is the space of P matrices, and some things I can tell you about its geometry is that this is connected, it's star-shaped, it's a cone, unfortunately not a convex cone. It is a semi-algebraic set if you take the perspective of viewing the complex numbers as like the real plane. And then I was able to compute the dimension of this as a semi-algebraic set. Great. So now I want to relax the conditions a little more about having your principal minors be non-negative to just being real, which is still maybe a little surprising given complex entries. And for reasons I don't want to get into, it's actually not that different to study real versus non-negative principal minors. And the reason I want to do this is because these things form a variety. So I get access to the tools of algebraic geometry. All right, so okay, I want to have time to talk about the last order case I understand. So I'm going to go through this a little quickly, but what are some sufficient conditions for a matrix to have real principal minors? Well, if the integers are real, certainly the principal minors will be real. And if your matrix is Hermitian, then certainly the principal minors will also be real. And this is kind of what usually happens in a good sense, in full measure inside of curly R, the space of R matrices. It's sort of these things and their orbit under group action. Yeah, so the gist of the next few slides is I have a good understanding of the irreducible components of the variety of these things. So if you're interested, I'm happy to talk about the details, but I really want to talk about the n=5 case. So I'm going to jump there. Okay, so what you learn when you look at the irreducible components of the n=4 case and think about how those can fit together is that the irreducible components of 5 by 5 matrices with real principal minors correspond exactly to red and blue colorings of K5, such that the red and blue subgraphs individually are Eulerian. So to show you some examples, if you color all your edges blue, this satisfies what you get, and this corresponds to Hermitian matrices, such as this one. If you color everything red, this corresponds to real matrices, but then there are more interesting things. So there are 7 isomorphism classes of these kind of colorings. So here's one, you can have a blue triangle, and you can check that the 7 edges of color red form an Eulerian graph. And this is a matrix realizing this type. So this is a point in the corresponding irreducible component. You can flip red and blue, and here's a matrix satisfying that. And here are 2 more. You can do 4 cycle that's red or flip the colors. But then here's an interesting one. So here the subgraphs are dual. They're this coloring is self-dual. If I flip it, I take red and blue 5 cycles and get red and blue 5 cycles. And this is the only one that cannot exist. And it's kind of fundamentally for reasons related to real algebraic geometry. There's a sum of squares obstruction, which I think is kind of neat. And I'll close by posing 2 kind of questions that I'm thinking about that if you're interested in, I would love to work on with someone. So the irreducible components for all the dimensions that I've been able to work out have been toric and characterized by the sort of type of the 3 by 3 principal submatrices. The real and Hermitian are the 2 kind of types. And toric geometry is nice for combinatorialists. That puts us in kind of the realm of polyhedral geometry. So I'm curious if that holds for higher n. And then I'm wondering also if I can parameterize these things in a way similar to known parameterizations of totally positive matrices by initial minors, or positive definite Hermitian matrices, which Rick Kenyon and Robin Pimentel have a really nice paper about parameterizing positive definite Hermitian matrices, among other classes, with principal and so-called almost principal minors. Thank you. That's all I have.
So in the examples you showed, this is a variety sitting in a real algebraic variety sitting in 50-dimensional space, and all components have the same dimension.
And they are not equidimensional, no. But it is in, yes, so it's the real points of a 50-dimensional, a variety sitting inside 50-dimensional space, yes. The two big components are like the orbit of Hermitian matrices and the orbit of real matrices. And then the other ones I showed where there's kind of non-trivial colorings of K5 are higher codimension. Can I take one more?
Yeah, I was just going to mention that one can also parameterize all matrices using principal and almost principal minor products. Conjecture of Pimentel and Kenyon, but we proved it in a follow-up paper of so I would expect the answer to your last question is yes.
Yeah, I would hope to find like a bijective parameterization, I guess, is like which principal and almost principal minors like do I precisely need, and then like what relations do I impose on them in addition to the sort of hexahedral relation that is like known to hold on them. Yeah.
First, thank you so much for the opportunity. And my name is Soyeon, and I will explain some basic concepts about braid variety and how we can splice them. The word braid is coming from the word braid group, and this is denoted by this BRN. And the braid group has generators called the Artin generator, and this Artin generators satisfy this relation, which seems to be similar to the symmetric group, but the only difference is that we are no longer having sigma I square is equal to identity, which was in the case in the symmetric group. And I will focus on some specific braid word from this positive braid group called the positive braid word. And the word positive means that I will only pick the ones that are the product of the Artin generator, but I will not allow any inverses. So I will consider something like sigma 1, sigma 2, sigma 1, but I will not consider something like sigma 1, sigma 2 inverse. So once I pick my positive braid word, my braid variety is indexed by this positive braid word. This is an affine algebraic variety, which is irreducible and smooth and having some nice property. And I will not give a precise definition here, but this is defined as a configuration of X in a geometrical sense. And we actually saw some classical examples of braid variety in Laura's lecture. I don't know where is Laura, but she already explained this Grassmannia and positroid variety, which was kind of like related to the Quebec graphs. And the braid varieties are best generalization of these imperturbable varieties. So people care about this braid variety for many reasons. Now I will explain what is a splicing map. So the splicing map is an open embedding of this x beta 1 tilde times x beta 2 tilde, but I made a typo. Going into this x beta 1 beta 2, concatenation of this beta 1 and beta 2. And this beta 1 tilde and beta 2 tilde are determined by this my beta 1 and beta 2. And my splicing map, the splicing map that we found is actually an isomorphism on this right and both sides. So they are kind of dimension preserving map. And we also conjecture that this map should be a quasi-cursor isomorphism. which is a kind of fancy word of saying that this map should preserve the essence of the geometrical essence of the Koefler algebra structure. So recent discovery of many other people showed that the braid variety admits a Koefler structure, and these Koefler structures are explained by the picture on the right called the weaves. And visually, our splicing map is kind of motivated by cutting the weaves. So once we cut this trivalent, like if we focus on each trivalent vertices in the weave, and if we cut along this dotted line around this trivalent vertices, they will give me a splicing map. So the top part, the sliced top part is corresponding to x beta 1 tilde, and the other remaining bottom part is corresponding to x beta 2 tilde, and the whole picture is kind of corresponding to x beta 1 beta 2. And now, and before I move on, I wanted to kind of say how this might be related to the summer school. So I'm kind of wondering whether braid varieties are positive geometry, and kind of also wondering how the splicing map could help proving that splicing map and Koefler structure could help that proving that they are positive geometry. And I also made a QR code, so if you're interested, you could also take a photo. And here is more references. Thank you for listening.
When you said a positive geometry, you meant there is the positive part, I mean, here of the braid variety with some positive.
Yeah, but the problem is that I don't think people study much about the totally non-negative part of the braid variety. Yeah, positive part.
Thanks so much. That talk is from Rowan. From the University of Southampton, not the University of Southampton.
What do I do with this? Sir? Oh,
So just the small mic, just include on your lapel and hold in your mouth.
Sure. Okay, so normally when I talk about this, it's to physicists who are very comfortable with what an amplitude is, not so much cluster algebras. I'm aware that there's the opposite issue here. So I'm not going to be particularly mathematically rigorous. Sorry for any improper use of terminology. I'd like to tell you a little bit about the sort of standard well-trodden connection between planar n=4 scattering amplitudes and cluster algebras, and to present some evidence that cluster algebras also have information encoded in them to do with essentially amplitudes beyond n=4, which lack the dual conformal symmetry. So first of all, just a quick review of how cluster algebras actually enter into the story. So it's well known that when you write down Feynman integrals to calculate an amplitude, they'll often evaluate two polylogarithms, classical polylogarithms, but also Goncharov polylogarithms, which can be defined iteratively. Now, it's very easy to show from the integral definition that they enjoy a sort of recursive differential structure, which motivates the definition of the well-known symbol map. So if you iterate the symbol map, what you're eventually going to end up with are words, tensor products of variables called the symbol letters, which tell you about the branch cut singularities. So for example, for a classical polylogarithm, you just get -1 minus the argument, and then a bunch of arguments. So these symbols project out a lot of information about the amplitude itself. So the first entry tells you about the location of a potential branch cut singularity. And if you chop off the first entry, what remains is the symbol across the discontinuity. So there's information about the analytic structure. And a nice thing about symbol level work is it essentially reduces things to a linear algebra problem, and you can potentially bootstrap the answer by realizing there's only one symbol which fits all the constraints you would want to have. So very quickly in terms of the kinematics and how this actually connects to what we see in the cluster algebra. So as Nima explained, you introduce your dual coordinates related to the four momenta encoding the kinematics. You pass to the spinor helicity variables that we saw earlier. And then from here you go to momentum twisters. So these trivialize the gram determinant constraint on the kinematics, and other nice things happen as well. So essentially they're sort of 4-component vectors. You've got the lambdas and also the mu's defined by the incidence relation. Now, the distance is squared, the x squared that Nima showed us we could write the kinematics in terms of ordinarily we'll evaluate to the Plucker coordinates, minus formed by 4 of these momentum twisters, but also 2 brackets contractions of the lambdas alone. But because in planar n equals 4, you have dual conformal symmetry, you actually only need the Plucker coordinate. So the 2 brackets cancel out. So this means we can refer to Grassmannian cluster algebra. So you have a quiver diagram, you mutate on a bunch of stuff, you get a load of A coordinates or X coordinates in the language that mathematicians often use. And the cluster algebra gives you 2 things. It predicts the symbol letters, so the singularities that can come up. And it also makes predictions about the adjacencies in the symbol. So in other words, which singularities can occur consecutively. So this is a really powerful constraint. It opens the door to bootstrap calculations, as I mentioned earlier. Now, the problem is if we go beyond planar n equals 4 theory, we're going to need not just 4-component Plucker coordinates, but we'll also need these angle brackets, contractions just of the lambdas. And a nice way to overcome this issue is to introduce the infinity bitwister so that you can still use 4 brackets to parameterize the kinematics. So for example, for 5-point scattering, you declare that if 6 and 7 appear together, that's not a Plucker coordinate with the 4 entries anymore. It's now an angle bracket contraction. And these would combine with the ordinary 4 brackets to parameterize the kinematics fully. And so essentially, if we're going to find a cluster algebraic underpinning here, we need a cluster algebra which can supply the 2 brackets and the 4 brackets, and partial flag varieties are a natural candidate. So you, for example, for 5-particle scattering, you can embed this in GR47 by starting from the standard initial cluster, freezing some nodes, and then you'll only generate things which either don't have 6 and 7 together, or have them together, or not at all, rather, so that you can interpret everything in the way described. So some evidence that this tells us something. First of all, symbol letters. So taking the 5-particle massless scattering example without dual conformal symmetry, there are 26 symbol letters in the alphabet, and this procedure, after using permutations, produces 25 of the 26. The one which you can't find from the cluster algebra interpretation actually seems to drop out of all the answers, so that it can appear in individual integrals, but not in full answers once calculated. It also works in terms of adjacencies. So the symbol letters which the cluster algebra predicts won't appear next to each other don't. And an even more non-degenerate prediction is the triples rule. So if you have 2 symbol letters which aren't allowed to appear next to each other, but they appear separated by 1, from the planar n equals 4 story, there's a standard way from the cluster algebra to infer the unique thing that can sit between them. And we see this as well as predicted by the cluster algebra associated to the partial flag variety. So similar stories beyond 5 points. It also seems to work for 6 points. We can generate many symbol letters. Similar stories for certain form factors. All the rational letters can be generated. But there are some issues. For example, if you go to 6 points, the cluster algebra is infinite. It's not clear how we're now supposed to be truncating it. And it's also not clear how to recover some of the so-called square root letters. So there's compelling evidence that these cluster algebras do contain information about non-dual conformal kinematics, but there are details to be teased out. And hopefully, if this can be understood, it can let us extend bootstrap methods beyond the standard domain of planar n equals 4. Thank you.
Any questions for Rod?
You go. Okay, so if I understand correctly, so you're looking at the n-particle amplitude, and then the symbols are expressed in the Plucker coordinates of the Z matrix.
Yes.
Right. So the Z matrix makes an amplituhedron, but it's a higher loop amplituhedron that sits in a flag variety.
I mean, here really all we're doing is looking at the symbol letters and where they appear in the symbol. So we're not necessarily.
Sure, but if my statement true, there's an amplituhedron related to this?
I'm not sure. I'm not sure I answered that question.
Because I was going to ask what is the vanishing of these cluster variables tell you about the boundary arrangement of the amplituhedron?
I mean, what complicates this discussion is that it's not just one sort of orientation of the flag. You have to permute on the particle labels, and so this makes notions of positivity and so on a lot more difficult to disentangle.
It's connected to what you just said. Since you need to have permutations of cluster variables of the flag variety, Does it mean that you can also capture some non-planar contribution, or have you seen that also in non-planar?
Yes, yes. So I mean, for example, for 5-particle massless scattering, non-dual conformal, you can get the non-planar letters by the same procedure. So yeah, you can capture non-planar things if you, depending on which permutations you use. One would prefer to use dihedral permutations only, but you can go beyond that. Yeah, you can recover non-planar letters.
Okay. Great. Let's thank all the speakers again. 13-minute break to get Simo set up for his next talk, and meet back here at 4:30.
It's